This leads us into the idea of half-life. Half-life is more than just a really cool arcade game. But anyway, I digress. I used to play this game called Half-Life. Anyway, half-life in science is the time it takes for half of a sample to disappear, all right? And so if you start with 1 mole of substance, the half-life is literally the time required to get down to only half of a mole. Now on the graph on the right there, this is a hydrogen peroxide decomposition. You're starting with 0.020 moles per liter, and the first half-life occurs when you get down to half that value, or in this case, 0.010 moles per liter. So you can see there, if you go down to the dotted line, that took 654 minutes to go from 0.020 to 0.010. So for this reaction, the half-life is 654 minutes. Once you know the half-life, then you can start figuring out quantities based on multiple half-lives. So what I mean by that is that 2 half-lives, all right, you would use twice the half-life time. So 654 times 2, 1,308 minutes. So it's going to take 1,308 minutes to go to 2 half-lives. You went from 0.020 to 0.010 to 0.0050 moles per liter. And you can see how there's this 654 interval between the different half-lives. So at 4 half-lives, you're at 2,616 minutes, etc., etc. In half-life analysis, you really never go to 0. All right, you never go to 0 concentration, moles per liter. And because we're dealing with 10 to the 23rd of these crazy molecules or atoms at one time, that's usually pretty reasonable. There are some exceptions, like sodium metal and water is incredibly product favorite, but more often than not, you get down to a very, very small quantity of the original stuff where it's basically considered reacted, and that's up for you as the scientist to decide when it really has all reacted or not. H2O2 decomposing to water and O2 is first order, all right? And so we're starting here with 0.020 moles per liter H2O2. After 1 half-life, which we saw in that previous slide was 654 minutes, we're down to half the original quantity. So that would be 0.0100 moles per liter. So knowing about half-lives, you can see then how long it takes. Notice that you're down to half of the original reactant concentration. After 2 half-lives, or 654 times 2, which is 1,308 minutes, you've now gone down to 1/4 of your original concentration. So 0.020 to 0.010 to 0.0050 moles per liter. So you can see this kind of curve that happens, and that's very, very common. If you go 1 more half-life, now you're at 1,962 minutes. You're at 3 half-lives. That's 1/8 of the original reactant, which is still around. Why stop there? 4 half-lives would be that 654 times 4, or 2,616 minutes. You can see that you're now down to 0.00125 molar. That's 1/16 of the original concentration. So half-life has some uses for it, but it's also interesting because you might at first think that, oh, these reactants will go automatically to 0. Well, not usually, and that's something we're going to start to explore both in this chapter and in Chem 223. Here's an example with how half-life can be really useful. Sugar fermenting, like all biology things, is a first-order process, and there's an enzyme being used as a catalyst. Enzymes are nature's catalysts. Our bodies have lots of them working around inside us right now. Pretty cool. But anyway, sugar plus the enzyme goes to some kind of products. We don't have to care about the products. Anyway, it's a first-order process, so rate equals K times the concentration of sugar to the first power. To the first power is usually ignored, so just sugar. Rate constant K, 3.3 times 10 to the minus 4 inverse seconds. Question is, what is the half-life of this reaction? Oh, geez. If you are familiar with video games, this is the picture of Half-Life, the game I used to play a lot. Half-Life 2, I know. I really need to grow up as your instructor, but anyway, I couldn't resist throwing it in. Gordon Freeman is the name of the dude there in the glasses. He's really cool. But again, that really has nothing to do with chemistry. My apologies. In the problem, going back to your regular scheduled programming, rate equals K times sugar, and K equals 3.3 times 10 to the minus 4. What's the half-life of this reaction? Now, this is kind of cool. If you're at a half-life, then R over R0, i.e. the amount you have left divided by the amount you started with, is going to equal 1/2. So if you started with 1 mole, you'd be at half a mole, and half divided by 1 is 1/2. But you could do it for any number. You started at 0.2 moles and you have 0.1 mole left, that would be a half-life, that would be 1/2. So regardless of where you are, R over R0 will equal 1/2 when the time equals half-life. T1/2 is the symbol for half-life. So if you do a little math here, natural log R over R0 equals minus KT. Well, natural log of 1/2 is negative 0.693. So negative 0.693 equals minus K times T 1/2. Remember, we're at the half-life, so that's why our T is T 1/2 here, trying to show. Now, obviously, the negative signs will cancel, so we end up with a super handy expression to convert a rate constant K into half-life or a half-life into rate constant. Now for this problem, we're trying to find the half-life. So 0.693 divided by the rate constant K is going to give us the half-life. Now initially, the rate constant K is in inverse seconds, so our half-life is going to come out in seconds. So when you take 0.693 and divide it by 3.3 times 10 to the minus 4, you're going to get 2100 seconds to 2 sig figs. And if you convert seconds into minutes by dividing by 60 seconds per minute, you're going to get 35 minutes. So 35 minutes is the half-life for this reaction of sugar decomposing. T1/2 equals 0.693 divided by K is going to be super helpful to us. So make a note of it. It's a nice way to go from half-life to rate constant or rate constant K to half-life. This process only works for first order, but there are some second order and zero order equivalents to this equation. I'll show you them here in a little bit. So here's a given first order reaction, and K equals 0.347 inverse hours. And the question is, what is the half-life of this reaction? Okay, answer E is totally silly. Dr. Gordon Freeman was the hero of that half-life game. My apologies again for the bad references in the media. But anyway, the important part here, half-life equals 0.693 divided by K. So what I would do in this problem is take 0.693 and divide it by 0.347, and that's going to get us an answer in hours. Remember that K and T have to be the initial amounts. So T1/2 initially will be a value in hours. And from hours, I have to convert it to make sense of the answers. I have to convert hours into minutes. So I'm going to need to multiply by 60. So if you do the math, 0.693 divided by 0.347, it comes out to be 2.00, but it's 2.00 hours because K was in inverse hours. So 2 hours times 60 minutes per hour, 120 minutes. The next kind of problem is one that you'll see sometimes in classes like this, and there are two methods to determine the answer. And one way I'm going to refer to as the Chem 104 method, because in Chemistry 104, this is the way we actually tell students to solve it. But the better answer is to use that integrated first order rate law. So without further ado, we're back to the example, rate equals K times the sugar, K 3.3 times 10 to the minus 4, and we saw that the half-life is 35 minutes. So let's say that we start now with 10 grams of the sugar. We want to know how much is left after 2 hours and 20 minutes. Okay, no problem. And remember, half-life 0.693 divided by K. Well, in Chem 104, what we would do is we'd try and figure out the time elapsed, and the time elapsed will be equal to some integral of 35 minutes. So 35 times 1, 35 times 2, something like that. If you figure out 2 hours is 120 minutes, 120 plus 20, 140. 140 minutes divided by 35 is 4. So that means 4 half-lives have passed in this problem. So after 1 half-life, you're down to half the quantity, which would be 5 grams, and that would be 35 minutes. And then 2 half-lives, 70 minutes, you'd be down to 2.50 grams. Third half-life, fourth half-life, you're at 140 minutes, 0.625. 5, 0.625 grams is the answer. And this way it's awesome if your time elapsed is a whole number equal of half-lives, all right, like exactly 4. If you have like 3.65 half-lives, then it doesn't work quite as well. So the Chem 222 method, which is what I recommend highly for this class, is you go back to that first order integrated rate law. Now, because K is in inverse seconds, we need to convert our time into seconds. Seconds and K have to be the same kind of units. So you'd have to convert 2 hours into minutes first, 140, and then 140 minutes times 60, that's 8,400 seconds. Then natural log R over R0 equals minus KT. K and T are both the same kind of unit, seconds. R0 is 10 grams. R is going to be an answer in grams. And if you solve for it, and got to take the anti-log once again, stuff like that, make sure you know how to do these kind of problems. If you aren't, let me know. I'll help you out. 0.625 grams. So same answer. Now, really, in this class, I recommend the Chem 222 method because it may look weird, but honestly, it will get you out of any situation. And some of these problems will be much more difficult using the quote-unquote Chem 104 method because you may not have exactly like 4 half-lives. You might have like 4.17 half-lives or something. Now, the Chem 222 integrated first order rate law works great in all of them. Half-life is super useful for radioactive decay. And we talked about earlier how all biological processes are first order and most chemistry processes are first order. I would argue that all radioactive decay is a first order process as well. So this is an example with tritium. Tritium is radioactive hydrogen. It's a very small component of all the hydrogen around us. But anyway, it breaks down into an electron and a helium-3 isotope. The half-life, 12.3 years. So let's say we have 1.50 milligrams of tritium. How much is left after 49.2 years? And again, the half-life, 12.3 years. Electrons in this case are actually referred to as beta particles. And we're going to talk about that more in the next chapter of Chem 222. But for right now, we're focused here more on half-life and how we can use half-life to solve equations like this. What I would do, go back to the first order integrated rate law. Natural log R over R0 equals minus KT. We know R0, how much we started with, 1.50 milligrams. The time elapsed, 49.2 years, all right? But we're in a problem because we're trying to find how much is left, which is R, and we don't have K, all right? But since we have half-life, if you remember, half-life equals 0.693 divided by K. Or in this problem, let's use K equals 0.693 divided by half-life. So in your calculator, 0.693 divided by 12.3, the half-life, that equals the rate constant, that holy grail of so many of these problems. And it's 0.0564 inverse years. Half-life was in years, so rate constant will come out to be inverse years. Well, now we can use this K value, throw it up there in the integrated first order rate law. Natural log R over 1.50 equals minus KT minus 0.0564 times 49.2. Now, initially, it comes out to be negative 2.77. You're going to take the anti-log of both sides in order to get the natural log R over R0 down to just R over R0, as we've seen before. That comes out to be 0.0627. And I do want to comment that the R over R0 is the fraction remaining. So of the R0 we had, that we started with, 1.50 milligrams, 0.0627 is literally the fraction of that amount that's going to be remaining. So if we take that number and we multiply it by the amount we started with, 1.50, we're going to be down to 0.094 milligrams of tritium. So you can see how we used half-life to find rate constant. We then plugged everything into the integrated first order rate law, natural log R over R0 equals minus KT, and solve for R, 0.094 milligrams is left. Here's a problem with radioactive copper-64. It's used apparently in copper-2 acetate to study Wilson's disease. But anyway, the half-life has a half-life of 12.70 hours. What fraction of the copper-2 acetate remains after 2 days? Now, first of all, I hope you're starting to see here that time has to be in the same kind of units. And we have hours and we have days, all right? So the first thing I would do here is I would probably convert 2.0 days into hours, 48 hours. That will allow us to use the half-life and the time elapsed in hours, same kind of unit. So the fraction remaining is the R over R0. So natural log R over R0 equals minus KT. T is going to be 2 days in hours, 48 hours. But we also need to take 0.693 divided by the half-life to find K. Then take the anti-natural log to get R over R0 by itself. So here's what it looks like. Natural log R over R0 equals minus KT. I turned 2 days into hours because the half-life was in hours. 0.693 divided by the half-life will give you the rate constant. I didn't even calculate it here. I just went ahead and plugged it right on in. So plug this all in, take the anti-natural log, e to the natural log to the x to get just the fraction 0.073. If you don't get that answer, you let me know. No problem. But you can see this is sometimes kind of useful for figuring this stuff out. When it comes to first order, half-life equals 0.693 divided by K. And 99% of the time, that's the one you're going to use in chemistry. If you do have a second order or a zero order reaction, the half-life looks somewhat similar, but you do need to worry about the initial concentration of the reactant, A0. So you have to know how much you started with, and it will affect your half-life. So half-life in zero and second order is a little bit different story. We're not going to focus too much on that in this class, but in future classes that may become important. But even if you had to in this class, just realize you do need that initial concentration of the reactant to solve for the half-life. Radioactive elements have half-lives all over the place. Some of them are super long and some of them are super short. So you can see there that uranium-238 breaks down into 234 thorium and some helium with a half-life of 4.5 times 10 to the 9th years. 10 to the 9th is like a billion, so that's 4.5 billion years. And that's just to get rid of half the uranium-238. So imagine how long things will take. Carbon-14 is involved with carbon dating, and they use the carbon dating half-life of 5,730 years to figure out the ages of a lot of historical documents and stuff like that. That's a number that pops up quite often, actually. Radioactive iodine-131 has a half-life of about 8 days. Element 106, named after Glenn Seaborg, one of my heroes, 0.8 seconds for it to decompose. And one of the newer elements, rontgenium, after the Rontgen guy that did X-rays, 0.0015 seconds. That's the kind of stuff like if I said, hey, look at my sample of rontgenium in my hand, and I opened up my hand, it would all be gone. And first of all, I shouldn't have it in my hand because it's obviously radioactive. It's an alpha emitter. We'll see in the next chapter. But anyway, you can imagine that this stuff, man, it doesn't last that long. And these are some of the newer elements they're finding. Very, very short half-lives, which means you just don't have the element around that long to study it. Medicine also uses half-lives, and drugs will have a half-life in your body, and it depends on age and lots of different substances. One kind of silly thing, but a good example, is the half-life of caffeine, 3.5 hours in the body. So I think I am perpetually above the 3.5 hours half-life threshold because I drink so much coffee. But anyway, you get the idea. They can use this in medicine to see how long they're going to last and stuff like that. This leads us into the idea of mechanisms, and mechanisms is another big part of kinetics, because in the rate law we just looked at extensively, we looked at how to find if things were first order, second order, zero order, stuff like that, rate constants. But the question you might be asking yourself is, why are some reactants first order, and why are some reactants second or zero order, stuff like that? Well, to answer those kind of questions, we really need to look at the mechanism, which is how you go from reactants to the products. Now, the rate law we saw had to be figured out through experiment. Like you've got to go in the lab, try different trials, stuff like that. The mechanism now is really purely theoretical. There's some ways to augment your ideas that you're coming up with theoretically, but really it's about theory. So it's a really cool combination of different things in science. As a useful idea of how this mechanism thing works, on the right-hand side is an example of a skiing area. I think it's a skiing area in Vermont, but I'm not totally sure. People, when they go skiing, they'll go from the bottom base lodge and they'll go up here to the top of the mountain. And from the top of the mountain, depending on your skill level, you can go down different ways. And for reasons which we don't need to go into a lot of detail here, I am a really bad skier. So anyway, if it was me, I would try and take the most gentle loop down because I don't want to go too fast and I'd probably still end up hitting some trees, but I would go down as gently as possible. All right. And then, finally end up way over here in Timbuktu, but eventually I would end up back at the base camp. All right. Now, I'm sure that some of you in this class are like basically world-class Olympians when it comes to snowboarding and skiing, something I've never been. So you'd probably go, straight down. Oh, my pen can't even handle it. It's too intense. But you would go like straight down the mountain. So all of us, you the cool Olympic person and me the pathetic skier, we would both start at the same point and we would both end at the same point. But the path we took to get there was quite different. Yours would have been direct, all right, highest to lowest, as fast as possible. On the other hand, lame me, I was taking, weird things and going through trees and stuff, trying to be gentle because I didn't want to go too fast, all right. Both of us got to the same point, but it was obviously a different amount of time to get there. And chemicals will do the same way. Now, normally we'd probably think chemicals would go the fastest way, but that's not always the case. We can use the rate law to see, are they really going the fastest way or are they going a slower way? And along the way, we can then make sense of what the rate law is trying to tell us, like why some chemicals are first or second. So we're really digging into the way that chemicals go from reactants to products, something we haven't done up to this point. And from that, we'll be able to learn about why the rate law is what it is. Mechanisms can be really important in chemistry. On the right is a graph that shows a reactant on the left and a product on the right, all right? And we have on the left a methyl isocyanide. It's a methyl group, CH3, and it's turning into a methyl cyanide. So this thing right here on the right is methyl cyanide, also known as acetonitrile, and this thing right here on the left is the methyl isocyanide. And methyl cyanide, which is also known as acetonitrile, is a little bit more stable than the methyl isocyanide. Now, the red line right there is the mechanism that scientists have proposed for how methyl isocyanide goes to methyl cyanide. And notice that at first, there's a lot of energy. This is an energy axis, okay? And it takes a lot of energy to get up to some kind of what we're going to call activated complex or transition state. And once you get up there, then you actually get a lot of energy back down as you go back down to the product. Now, if you look at these little pictures, these are essentially kind of Lewis structures, but only the first and the last structure will really make any sense. We've seen in the Lewis structure chapter that if you have a triple bond and a single bond, the electron pair geometry will always be linear, 180 degrees across. And you don't see that on the second picture, which is right here, or the fourth picture right here. You've got more what looks like kind of a 120 degree angle. So you're starting to see some really weird things. But if you really want to be freaked out, like in a science fiction kind of way, look at this bad boy. Carbon is connected directly to the triple bond of the CN triple bond cyanide part. And that doesn't make any sense. So a coordination diagram like this is trying to make sense of why isocyanide wants to go to cyanide. And what scientists propose is that the cyanide starts to kind of go up. So the carbon starts to go more 120 and even 90. And that's not going to be a real stable configuration because normally that wants to be 180 degrees apart. So the cyanide essentially shifts down. The triple bond is connected to the carbon bond, which is really, really weird from all the rules we've studied. And then because that's not going to stay that way, the carbon finally ends up connected to the other carbon, but at 120 degrees or something like that. And finally, then it straightens out to 180. Beginning part and ending part will make sense on everything we've seen, but these intermediates in between are going to be all over the place. The highest energy part is called the activated complex, and you're going to see really weird things there. So carbon connected to a triple bond, that's like, whoa, bizarre, man. But it's necessary to understand how reactants go to products. E sub A is going to be important for us. That's the energy of activation, and that's the energy to get up to that activated complex, to get to that super wild part. And finally, the difference between where you start and where you end up, i.e. reactants and products, is going to be a delta E. If that delta E is lower, like it is right now, that means this reaction is exothermic. You're ending up with a lower energy state than you started with. So energy was given off. This is an exothermic reaction. But finally, you can also, at least intellectually, think about going from products to reactants. So methyl cyanide back to methyl isocyanide. You'd have an even bigger E sub A because you'd be starting down here and you'd have to go all the way back there. And at the end, your resting spot, the isocyanide, is higher energy than where you started. That would be endothermic. So these reaction coordinate diagrams, super cool. And we're going to dig through everything I just said in more detail in the next several slides. This picture here shows the difference between the reactants and products energy. And because in the way we're looking at it, reactants on the left, products on the right, which is the most standard by the way, the final energy is lower than the initial energy. Energy was released. So in this example, the energy of the final was less than the energy in the initial. Energy is released. This is exothermic. But again, if you had it the other way, if reactants were lower in energy than the products, you could have an endothermic reaction. The high point, though, in that diagram shows again what's called the transition state or the activated complex. And at those times, you're going to see the most breaks from all the standard rules we learned in the Lewis structures than we ever had before. That transition state, like kind of chemical looking formula right there, it's called the activated complex. And you're going to see some really wild interactions. You'll see carbon with 5 bonds, which I told you never can happen. In this example, you're looking at carbon bonded to a triple bond, which also doesn't make sense either. So you're going to see really wild combinations. These are super high energy transitions that don't exist by themselves. But if you're going from reactants to products, maybe it's worth it for the molecule to make that cost to get the energy out on the other side. The energy gap, E sub A, between where you start and the highest point in that activated complex is called the activation energy barrier, or the energy of activation. And that's a super important number for chemists. If the K constant was the holy grail of the last section, E sub A is going to be the holy grail of this section. Because knowing about differences in E sub A, you can oftentimes rationalize why reactions are faster and slower. And we'll see that coming up. To understand this energy of activation barrier, I want to use some kind of cheesy real-world examples to show you some of the things that happen. Now remember, all these chemical systems, there's like 10 to the 23rd little molecules bouncing around at one time. So I've got there in the lower part a golfer, all right? And she's trying to get the golf ball over the hill to the hole on the other side. Well, you can imagine that it would be super easy to not hit the ball hard enough. So the ball would like start to go up, but then it would come back down, all right? On the other hand, it's super easy to hit it like too hard, so maybe it would go wider over. The idea is to get just the right amount of energy to get over the hill, and that's where skill comes in and all that kind of stuff. So energy of activation is kind of like that. You want to have just the right amount of energy. And not all reactant molecules will have the right amount of energy. They'll kind of go up a ways, but then they'll go back down. They need enough energy to make it happen. And they might do it a couple times too before it happens. Same thing in the volleyball example. When she's hitting the volleyball there, you have to have just the right amount of energy and the right direction, of course, to get the ball over the net. And if it's not enough energy or the right orientation, it'll just bounce right back. And of course, that's not what you want. So chemicals will do that too. They have to have the right amount of energy, the right amount of direction to get over the energy of activation barrier and become a product. So what that means is not all reactants instantly become products because they don't have the energy and or the direction. Differences in activation energy can be the difference why reactions are fast or slow. If you have a really low energy of activation barrier, then you're more likely to get over the barrier and the reaction will go faster. On the other hand, if you have a big energy of activation barrier, it may take many, many times to get over the barrier, and that's going to make your reaction slower. So one reason why reactions are faster or slower is just the depth or the height, I guess, of the energy of activation barrier. Generally, as temperature increases, so does your reaction rate. Reactions go faster at warm temperatures, and that's really because the value of K, the rate constant, is temperature dependent. So all of the ways we saw earlier to solve K, you could solve them at different temperatures, all right, and you'd have different values of K. So this graph here in the lower left-hand corner, it shows a bunch of rate constants K on the left versus their temperature on the right, and you can see how the value of K is increasing as the temperature gets up. Now, changes in K will help us to find the activation energy barrier, and that's a pretty cool thing.
A solution containing hydrogen peroxide is added to one containing iodide ion and ascorbic acid. This is a clock reaction, where after a small initial fraction of the hydrogen peroxide has reacted, a color change occurs. The same reaction can be performed at low temperature. Under these conditions, the color change occurs after a longer period of time.
This reaction is called the iodine clock reaction. When I2 iodine forms, it makes that kind of dark purple kind of color. And you can see that without ice, it took 54 seconds, but with the ice bath, it took 1 minute and 31 seconds. So generally speaking, reactions do occur slower at the lower temperatures, all right? When you lower the temperature, the individual molecules don't have enough energy to jump over the energy of activation barrier. So it takes them more time to get over it. On the other hand, warmer temperatures, they have more energy. It's easier for them to make the transition, in this case, to the kind of dark iodine color. So if you're going to make bonds, or break bonds for that matter, the reactions have to have, like we talked about, the right energy of activation or activation energy, but they also have to have the right geometry, all right? Like it would have been easy for the golfer earlier to hit it with, the right energy, but if it was in the wrong direction, it might go to another golfing hole or something like that. In a chemistry world, this is also really important. So I want to show 3 videos here, and they're all about the reaction of ozone and nitrogen monoxide to make oxygen and nitrogen dioxide. One of the videos will show when the molecules come together, but with insufficient energy to make anything happen, like you don't have enough energy to break bonds and make bonds. One of them will be the right energy, but the incorrect geometry. And then finally, we'll look at a video where you do have the right energy and the right geometry.
For 2 molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate without reacting.
When I give lectures face-to-face, I always come in and I try and have enough energy that I can really jazz my audience, all right, so I can get people excited about chemistry, because don't tell anybody, but sometimes chemistry isn't the most exciting. Anyway, this is kind of, in this particular problem, it's imagine you have like a bunch of tired students and a tired instructor. They're just not enough energy, man. No one's getting jazzed about anything, and it's not going to be the most efficient learning tool. Let's look at an example now that's not about insufficient energy, but insufficient geometry, or the incorrect geometry for this reaction to occur.
If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
In this reaction, the nitrogen must collide with an oxygen on ozone to make the NO2, all right? So in this problem, there was enough energy, but it was the oxygen on NO colliding with an oxygen on ozone, and that's not what you need to make the nitrogen dioxide bond. The nitrogen's in the middle of the two oxygens. You can draw the Lewis structure. So this is an example where the energy was right, but the geometry was wrong, and you're not going to be able to make a molecule or the products in this case with this incorrect geometry.
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
So on the right there is an energy diagram or reaction coordinate diagram for what could be this interaction. All right, there's going to be a reactants, I'll just draw it R on the left, and products on the bottom. All right, whoops. There we go. And initially, in the first example, there wasn't enough energy to overcome the E sub A, that energy requirement to make reactants turn into products. And in the second video, the energy was there, but they weren't oriented right. So you can't make the transition state, whatever it is, to make it happen. But in this third example now, ozone and NO were in the right energy, in the right geometry. They were able to overcome the energy of activation barrier, i.e. the NO was able to pull an oxygen from ozone to make NO2, and you ended up making products. Now, this reaction is definitely exothermic, and it's exothermic because the final energy is less than the initial energy, so the E sub A value is like a cost you have to pay to get in, but then you get a lot of energy out. There's nothing wrong with thinking about these reactions in the reverse. So you can see that there's an EA forward, which is what we've been kind of talking about in this problem, but there could also be an EA reverse. Like, what if you wanted to make more ozone? You wanted to take oxygen and add NO to it to make ozone and NO. Well, you absolutely could. It would have a very big energy of activation. You'd have to go from the bottom where the now products are sitting, but it would be reactants in our case. It would have to go all the way back up to that transition state. The NO would be essentially giving up an oxygen to make ozone, and NO would be by itself. And then at the end, you'd end up where the reactants are in terms of energy. So that would be an endothermic process with a very large energy of activation. So we would probably predict then that the forward reaction is more likely than the reverse reaction because of the different energies of E sub A. And it's quite a bit different, it looks like. So it's kind of cool to think about how these things work out. It is possible to calculate those energy of activations, forward, reverse reactions, whatever. And we can do that because remember that reactions are generally slower at the lower temperatures. They don't have enough energy to make it over the barriers, and they're generally faster at the warm temperatures. So you can have then these kind of pictures we've seen since the gas laws of showing the different distributions of energies, all right? Let's pretend that this black line right here, kind of in the middle, this is the minimum amount of energy required to make products. So there's more molecules at the warmer red temperature than there are at the colder blue temperature. Some of the blues will have enough energy to become products, but more than there'll be a lot more at the warmer red temperature. And again, differences in activation energy are oftentimes the difference why reactants are slow or fast. But if you have a warmer temperature, you have a bigger fraction of molecules able to overcome that energy of activation and become product. So this guy named Arrhenius studied this in quite a lot of detail, and he came up with what's called the Arrhenius equation. And it looks kind of funky at first, so let's kind of dig through this here. The rate constants K we've seen and talked about do vary with temperature. And so what Arrhenius came up with is how rate constants K equal a big A, and that's called the frequency factor. And frequency factor is related to the frequency of collisions with the correct geometry. There's more you can do with that, but we're not going to talk about it too much in this class. But anyway, big A frequency factor times E, that's the anti-natural log E, E raised to the power of negative EA over RT. And the cool part for us right now, if you can call it cool anyway, is that, hey, here's E sub A. This is a way to calculate E sub A from values of K. E sub A is a constant. Temperature is changing along with the rate constants K. So A, big A, E sub A, and R are all constants. R here is what I called the energy R in an earlier lecture. It's 8.3145 joules per mole Kelvin, or what's usually done in these problems, 8.3145 times 10 to the minus 3 kilojoules per mole Kelvin. But anyway, this equation is an exponential form, and if you're cool with math, you can use this in all the ways we've seen. But what scientists will usually do is take the natural log version of all that stuff. And you can do this on your own later if you'd like. But when you do that, you can rebrand, if you will, that equation as natural log equals negative EA over R times 1 over T plus natural log of A. And if you're like, Russell, you have totally lost it, this doesn't look any easier than it was before. Well, yes and no, because this new way of writing it here is like a straight line. It's Y equals mx plus b. M is the slope, all right? Negative EA over R equals the slope, which is a cool way to find the energy of activation. And B is related to the frequency factor. B equals the y-intercept equals natural log of A. So if you take a whole bunch of rate constants K and plot them as natural log of K versus 1 over their Kelvin temperatures, you will see a straight line. It'll have a negative slope. Negative slope equals negative EA over R. E sub A is how you find it. And E sub A is always going to be a big positive number. We will do this in lab. It's not hard. It's a little tedious. I won't deny it. But it's totally the best way to find these energies of activation. If you're curious about that frequency factor A, there's different ways to interpret it. And this is one version that I've seen a lot of information about. This is one way to interpret what the frequency factor is. And you can see it's basically equal to two exponential functions. K sub B is called the Boltzmann constant. It's basically the energy R constant, but per molecule. Temperature in Kelvin, there's Planck's constant, we saw in Chem 221. Delta S is the entropy of activation, and entropy is related to something we're going to talk about more in Chem 223. Entropy is kind of the measure of disorder, and we'll talk about that later. And then there's R again, the energy R value. We're going to see, again, more about entropy in Chem 223, but just realize there's stuff you can do with A. I will not be asking you any of these parts, like how to find the entropy of activation, but one day maybe you will want to, and it might be nice to see this in advance. A mechanism, then, is just the sequence of events that describes the actual process on how those reactants go to products. Like, how do you go from the top of the snow lifts down to the base lodge? Sometimes reactions are going to happen in one step, and sometimes they'll take several steps. Each of the steps, whether there's one or several of them, is referred to as an elementary step. And I'd like to show you a video now of an elementary step reaction. This is a one-step reaction where fluoride is displacing chloride. You end up with a fluoromethane, even though we started with a chloromethane.
When a fluoride ion approaches a methyl chloride molecule, a bond begins to form between the fluoride and the carbon. The molecule's carbon-chlorine bond lengthens and becomes weaker. The energy of the system increases. As the carbon-fluoride bond forms and the carbon-chlorine breaks, a configuration of maximum energy is reached, called the transition state. As the reaction proceeds to completion, the energy of the system decreases.
Notice that transition state. There were actually 5 bonds around carbon, 3 hydrogens, and there were dotted lines to both fluorine and chlorine. That's definitely a transition state where the activation energy is highest because carbon doesn't like to have 4 bonds, and it certainly doesn't stay there very long either. This reaction is exothermic because the product's energy is lower than the reactant's energy. If the product's energy would have been higher than the reactants, it would have been endothermic. Finally, because there were 2 reactants, the fluoride and the chloromethane, we would call this a bimolecular reaction. Bi, in this case, means 2, so 2 pieces come together to make products. Bimolecular is what you'd refer to it as. The molecularity of the process just says how many pieces, molecules, atoms, whatever, are involved in the elementary step. Now remember, most reactions we're going to look at will be single steps, but you can have more than one step too. So if you had just one piece breaking down to many pieces or more than one piece, it would be referred to as unimolecular. Down there you can see the very first one in that list. Unimolecular means A is breaking down to products, but there's only one reactant. Okay, bimolecular means you're going to have at least 2 pieces coming together to make products, and they can be the same, like A plus A. They could also be 2 different things, A plus B, all right, and those are all possible. Once in a while, you'll have termolecular, which means 3 pieces coming together, and they can all be the same. They can 2 of them be the same and 1 different, or they can all be different, whatever. Notice the rate laws. Because these are elementary reactions, single steps, rate law literally equals K times whatever the reactants are. This only applies, again, if it's a single step. Some reactions do occur in a single elementary step, but most reactions do take a sequence of individual steps to make the overall version. So again, that fluoride reacting with chloromethane, that was a single elementary step, and those are pretty cool. But most reactions, like this ozone breaking down to oxygen reaction, it's a series of elementary steps. So ozone breaking down to oxygen has been studied extensively, and what they feel is that it's a 2-step mechanism. The first step, which is unimolecular, is ozone breaking down to oxygen and an oxygen atom. And oxygen atoms are pretty reactive because oxygen likes to be a diatomic. Have no fear of, ice clear brew, oxygen was the of, okay? So that oxygen atom reacts with a second ozone molecule to make 2 oxygen molecules, 2 O2s. So the overall reaction is 2 ozones making 3 O2s. And notice there that the oxygen atom appeared and disappeared. We'll talk about that in a little bit.
Gaseous ozone decomposes in 2 steps. First, 1 oxygen atom splits off. Next, the single oxygen atom reacts with a second ozone molecule to produce 2 molecules of O2. The product of the overall reaction is 3 O2 molecules.
When you're writing an energy diagram for a multi-step mechanism like this one right here, every step has a hump in the diagram. And so you can see in the picture on the right there, this has 2 humps. And the first hump would be for step 1. The second hump there would be for step number 2. And so the energy of activation is usually, for us anyway, going to be the first hump's energy, so the arrow that's up and down right there. But it could be the second one too, and those special examples of that. So again, every step has a hump in the diagram, and the number of humps will tell you how many steps are in the mechanism. This is exothermic. Once again, reactants are at a higher energy than products, or products are lower energy than reactants. Exothermic.
Hydrazine is formed in aqueous solution in a 3-step process, each step being bimolecular. First, a molecule of ammonia reacts with a hypochlorite ion to form chloramine and a hydroxide ion. Next, the chloramine reacts with a second molecule of ammonia to form a charged species with a nitrogen-nitrogen bond. Finally, the charged species reacts with a hydroxide ion to form hydrazine and water.
There are lots of reasons why you shouldn't add bleach to household cleaners with ammonia. Lots of them, and you can look them up online. But one of the reasons is that the two of them together can make hydrazine, N2H4, which is actually a type of rocket fuel. Now, most household cleaners have ammonia, NH3, and the active ingredient in bleach is a hypochlorite ion, which is OCl-. So what you're seeing here is the reaction of two ammonias and hypochlorite to make hydrazine, water, and chloride, the part there at the bottom in yellow. Now, if I was just to show you the diagram on the right, you can see that there are three humps, all right? 1, 2, 3. And those three humps, and again, maybe I should highlight them. 1, 2, 3. Those three humps mean there's a three-step mechanism. And so what they propose is that the first step is ammonia reacting with hypochlorite. It makes a compound called chloramine, NH2Cl, which is super nasty, plus some hydroxide. The second step, that chloramine, is pretty reactive, so it reacts with another ammonia to make a protonated hydrazine, that N2H5 plus thing, plus chloride. And that protonated hydrazine will react, in this case with hydroxide, to make regular hydrazine and water. So the overall reaction here, two ammonias and hypochlorite make hydrazine plus water plus chloride. So again, pretty interesting. Three-step mechanism, three humps. This is also exothermic, going from reactants to products. Again, no adding bleach to any household cleaners. It's not good. This is only one of the bad reactions, believe it or not, that can happen. So be careful. Don't do this at home, kids. The rate determining step, the RDS, is the most important step when there's more than one step in a mechanism. And the rate determining step is literally the slow step. And it's the slow step which determines how fast the reaction goes, which is interesting. But even more importantly, because it's rate determining, the rate law, all right, remember how we use the rate law to find out first order, second order, zero order reactant, stuff like that? The rate law will tell you what reactants are in the rate determining step. So here's an example of that iodine clock reaction. It's two iodides plus hydrogen peroxide plus 2H plus acid, making the blue purple iodine, I2, plus two waters. The rate law for that reaction is rate equals K times iodide times H2O2. Notice that both iodide and H2O2 are first order reactants. So for the mechanism, that means the slow step is going to have one iodide and one H2O2 coming together. The slow parts are in the rate determining step, all right? And the rate law will tell you what the reactants are. So in this reaction, because the rate law, first order iodide, first order H2O2, that means in the rate determining step that there's going to be one iodide and one H2O2 coming together to make something else. So you can make just about any mechanism you want. Multiple steps, single step, you can have cosmic rays, whatever, but you have to have the rate law reactants correspond to your rate determining step in your mechanism. Otherwise, your mechanism isn't worth anything. This is also why the rate law orders of reaction are not necessarily the same as the stoichiometries. So if you look at this reaction, the iodine clock reaction again, it's two iodides plus hydrogen peroxide, but in the rate law, iodide was not second order, it's first order. So the rate law says that at the slow step, one iodide reacts with one H2O2. You have two iodides, but the second iodide is involved in a later fast step. Only the slow rate determining step has one iodide and one H2O2. So don't necessarily think that the stoichiometries of your reactants will equal the rate orders. It all depends on the rate determining step and the rate law. So here's the iodine reaction once again, and a scientist has proposed the following mechanism for this reaction. And notice here how we have step 1, step 2, step 3, but also we have slow step, and fast step, all right? And that's good. The rate law, which had to come from experiment, showed iodine was first order, H2O2 was first order. And sure enough, in the slow step, step 1, there's 1 H2O2 and 1 iodide. So in this reaction, in this mechanism, the 1 H2O2 and the 1 iodide makes hypoiodous acid, HOI, which is a weak acid and a weird one, plus hydroxide. And then the hypoiodous acid reacts with the second iodide to make iodine, I2, plus hydroxide. And then finally, the third step, hydroxide plus H plus making water. This is classic acid base and no problem. Well, if this is a good mechanism, then all of the steps together should give you the overall reaction, this one up here. So let's do this real fast, all right? Hydroxide and hydroxide on the product side cancel the two hydroxides on the reactant side. HOI cancels this HOI. We have H2O2, which is good, just one H2O2. We have two iodides, which are right there. We have two H pluses, which are right there. That makes iodine and two waters, which are both right there. Hey, that part of this mechanism is good. All of those individual steps combined together give you the overall reaction. But the other thing you have to have, this is a good mechanism, is that the slow step must correspond to the rate law reactants. So the slow step here should have one iodide and one H2O2, and it does, all right? That's what's in the slow step. This is a pretty good reaction, all right? The H plus is not involved in the slow step at all. H plus is considered a zero-order reactant. So let's stop right there. Zero-order reactants are still important for the chemistry. Like making the iodine clock reaction happen, you must have H plus, but they're part of the fast steps. So the H plus is zero order. Rate law means what is slowing our reactions down. And in this problem, the rate law is the iodide and the H2O2. The H plus is needed, but it's involved in the fast steps, not as important. So the bimolecular slow step is reflected in the rate law. And if all the steps together give you the overall reaction, which we did, we figured out, and if the rate law reactants equal the reactants in the slow step, which they do, this is a legitimate mechanism. So again, if you don't have both of those things followed, where you add all the steps and they give you the overall reaction, and the rate law reactants and the slow step reactants are the same, then you won't have a legitimate mechanism. But this one is legitimate. We checked them both. We are good to go. The reaction of NO2 and CO is thought to occur in two steps. There's a slow step and a fast step. So knowing that that's the proposed mechanism, and if the mechanism is legit, which of the following rate laws would correspond to this mechanism? So again, the punchline here is that the slow step reactants will be the ingredients, if you will, of the rate law. And if you look at that slow step, two NO2s are coming together, and there's no CO. So if there's two NOs, you could write this as rate equals K times NO2 times NO2, or if you combine the two NO2s together, rate equals K times NO2 squared. NO2 would be a second order reactant here. And notice here that CO didn't appear until the fast step. So CO would be considered a zero order reactant. Step one, again, is considered the RDS, the rate determining step. The slow step is what determines how fast a reaction goes. A reaction is no faster than the slowest step. So in the hydrogen peroxide reaction, turning into the iodine, which is the clock reaction, step 1, bimolecular. And again, the rate law says the iodide is first order, H2O is first order. That says that the slow step should have 1 iodide and 1 H2O2. And you can see in this slow step, that's exactly what we've got. So this is a good mechanism. Another comment should be made about HOI and OH minus. HOI and OH minus appear and then disappear, and those are called reaction intermediates. They're species that are around for a little bit, but they're used up right away. And if you have a mechanism and someone doesn't like it for some reason, you will bolster your argument for your mechanism if you can detect HOI and or OH minus. And they might be around for just a little bit, but if you have someone that's really good with lasers in chemistry, they can often detect these intermediate species for just like milliseconds or even nanoseconds at a time. So intermediates can be really important. An intermediate will appear in a mechanism and then disappear before the reaction's done. So in the overall stoichiometry, you don't see any HOI or OH minus for that matter. So mechanisms can be really cool. A catalyst sometimes will appear in a mechanism as well. Catalysts are usually used up at the beginning and regenerated at the end. Catalysts also don't appear in the overall stoichiometry of the reaction, but they will be used up right away and then recreated at the end. Intermediates are created usually right away and then used up towards the end, so it's a little bit different. So this is a possible mechanism. There's 2 possible choices here. And what's happening here is they're substituting of an iodide by a chloride ion. So if you see here, one of the final products is CH3Cl, and you start with CH3I. So you can imagine that mechanism 1 and mechanism 2 are coming from 2 different chemistry labs, and they're kind of having an intellectual discussion about which one it is. So you can see that in mechanism 1, the slow step is the methyl iodide, CH3I, breaking down into some weird stuff, and then that reacts with chloride to make CH3Cl. In mechanism number 2, the methyl iodide is reacting with chloride directly to make a CH3ICl, a 5-coordinate carbon species. That's going to be slow because that's not easy to do, but that will then subsequently break down further into methyl chloride and iodide. So what they find in people when they actually measured then the experiment part is they found that the methyl iodide is a first order reactant. So rate equals K times CH3I to the first power. And notice that there's no chloride. So if chloride isn't part of the rate law, that means that the chloride is a 0-order reactant. And if you have a 0-order reactant, 0-order reactants are not part of the slow step. So what the rate law here is telling us is that in the slow step, you will have one CH3I only. That's the only thing you're going to have. And if you look at those mechanisms, mechanism 2 would have methyl iodide and a chloride. So if the rate law would have been first order with chloride instead of 0 order, mechanism 2 would have made more sense. But in this problem, no way. Mechanism 1 is the way to go. Methyl iodide is first order, and chloride is then by default 0 order, which means it's not part of the chemistry. Mechanism 1 in the slow step has just a methyl iodide. Mechanism 1 is the one that I would put my money behind. That makes the most sense based on this data. Mechanisms have many uses, and in organic chemistry, you're going to see a lot of the uses of mechanisms. They can be used to explain products and products distribution. I want to show 2 examples here of what are called SN1 and SN2 mechanisms. SN stands for substitution nucleophilic. Let's just watch the videos and see some of the cool things that can happen.
In the unimolecular SN1 mechanism for a nucleophilic substitution reaction, the bond between the carbon and the leaving group breaks prior to formation of the bond between the carbon and the entering group. In the bimolecular SN2 mechanism for a nucleophilic substitution reaction, the formation of the bond between the carbon atom and the entering species occurs simultaneously with dissociation of the bond between the carbon and leaving group.
You'll see more SN1 and SN2 material in organic chemistry, as well as some elimination mechanisms, the E1 and E2, and lots of other different things. Very, very useful when it comes to higher parts of chemistry. Catalysts are really important in chemistry as well. And catalysts, what they do is they make reactions go faster. And they make reactions go faster by essentially lowering the energy of activation. So you can see on the left versus the right, it's a catalyzed pathway versus an uncatalyzed pathway. So on the left, they threw a catalyst in. The energy of activation barrier, the height of E sub A, was certainly lower than the height of the uncatalyzed pathway on the right. And that's an example of what the reaction does without the catalyst. Catalysts always are used up and they're recreated at the end. So when you have a catalyzed pathway, you will have two bumps in the pathway. You can see on the right, that was a single step, only one hump, if you will, in the pathway. But E sub A, when it's lowered, does make the reaction go faster, and that can be very, very important. If you make a good catalyst, you can literally become a millionaire, all right? Because, wow, having the right catalyst can be the difference between making a lot of product versus just tiny amounts at one time. So go into catalysts if you want to make money.
In a platinum-based catalytic converter, nitrogen monoxide molecules in the exhaust stick to the surface of the platinum. The molecule decomposes, each atom remaining on the surface. When another NO molecule comes to the area, it also decomposes, and its N atom bonds with the other N atom on the platinum surface. The O atoms also combine. The gaseous nitrogen and oxygen molecules then float away from the surface. A significant source of air pollution in many cities is the emission of nitrogen oxides by gasoline engines. The problem is not as severe as it was a few decades ago, due largely to the advent of devices called catalytic converters installed in automobile exhaust systems.
In the old days, like the 1970s for that matter, smog was a real problem, especially in heavy industrialized, high population areas like Los Angeles, stuff like that. A catalytic converter is a type of a wave that you can remove the carbon monoxide and nitrogen monoxide from a car exhausts and make better for the environment, arguably, CO2, N2, and O2. And the catalytic converters oftentimes use platinum, nickel, compounds, palladium, stuff like that. So they're pretty expensive, but man, the effect on the environment has been fantastic. And having a catalytic converter for gasoline production cars is pretty critical, I would say, for us. It also creates less problems breathing for people that are sensitive to that kind of stuff. Making polymers, which again is a huge part of industry, almost always involves some type of catalyst as well. And again, polymers are when you take things like ethene and turn them into polyethylene, stuff like that. Pretty cool process. You can make acetic acid from methanol using the right catalyst. Carbon monoxide can be inserted between the carbon on the methyl group and the hydroxide OH part to make acetic acid. And then definitely, like I mentioned briefly before, all of the enzymes that you might be hearing about in biology if you're taking that class. Enzymes are just biological catalysts. They're able to make a lot of life processes a lot easier, which is pretty cool.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
Manganese 4 oxide, aka MnO2, aka manganese dioxide, which I don't like as much. But anyway, MnO2 is a real common catalyst for a lot of species. Most of the transition metals that are catalysts, they'll involve electron transfer temporarily to another species, and then they get the electrons back. So in manganese's case, I don't know for sure on this mechanism, but I would guess it's going from a manganese 4 maybe to a manganese plus 2, and then somewhere it goes back to manganese plus 4 to make MnO2 again. But again, if you have a catalyzed system, remember that it's a multiple hump system. So the black line with the higher E sub A, that's the uncatalyzed reaction. So hydrogen peroxide decomposing by itself into water and oxygen. With a catalyst, you will certainly have more than one hump, probably two. In the first hump, the MnO2 is somehow used up, and in the second step, somehow the MnO2 is recreated. The reactants and products energy are the same, so this is exothermic either way, but it takes a lot less time because E sub A has been lowered quite a bit relative to the uncatalyzed reaction. Lower E sub A, faster reactions generally. This is a reaction where you can take iodine as a catalyst, and it can turn cis-2-butene into trans-2-butene. So this thing right here is the cis-2-butene, and on the far right you have trans-2-butene. It doesn't state it explicitly, but that's what's happening. And there's several steps, and this has been studied quite a bit. The first hump is iodine, I2, going to iodine atoms, iodide, and then the iodide goes to the double bond. It basically breaks the double bond. So at the highest point, one of the iodines has broken the double bond completely. And if I remember right, the carbon, either one of them is deficient or they're both sharing. This stuff gets really science fiction in the middle. But anyway, by breaking the double bond carbons can twist. So cis goes to trans, the double bond reforms, iodide atoms go back to iodine, and you end up on the product side. Again, overall reactants and products energy, it's exothermic because products are lower energy than reactants, but the uncatalyzed reaction, pretty tough to do. All right. I think it was like 240 kilojoules per mole we saw in an earlier lecture to make that transformation possible. But if you add a little iodine as a catalyst, you get the catalyst back, and it only takes 115 kilojoules per mole. And that's a lot easier than a 240 kilojoule per mole or so value. That's the end of Chapter 12 in kinetics. I really appreciate you spending your time with me. It's most appreciated. For more assistance in these sections, I do recommend you look at the study guides, which are bulleted, highlighted overviews of the different concepts from this chapter. The concept guide will have worked problems that go along with it, and kinetics, that might be a good idea to check out because there's a lot of kind of weirdness going on with these. Right after these notes, there are some important equations that kind of follow this slide. Those are kind of the overview of some of the more important equations from this section. And after that, there's a series of problems from this particular chapter. Problems are on one page and the answers are on the next. Try and do the problems yourself. See how you do. If you get stuck, let me know. If you do need help on anything from chapter problems to, what is molarity, which is fine. There's no dumb questions in my class. If you have a question on anything, be sure to reach out to me. My email is mike.russell@mhcc.edu. You can also email the Learning Success Center /Avid Center, and they can help you out as well. No problem. You don't have to do this stuff by yourself. All right. Thanks again for spending your time with me. Good luck with your studying, and have a wonderful day.